Hello friends, today we will discuss another kind of filtering, that is optimal filtering. In this particularly we will discuss about the Wiener filter. Wiener filter provides optimal filtering by taking into account the statistical characteristics of the signal and noise. The output of the designed filter should guarantee the best solution under the conditions imposed and the information provided. We can say it should be optimized with respect to some desired characteristics. Now, which is that desired characteristics for which we have to design or we have to produce the optimum results? What are the conditions required to design such filter? So, one such condition which we should consider before designing a Wiener filter is that the signal and noise should be independent, stationary, random process. Wiener filter is a single input, single output, finite impulse response filter with real input signal values and the real coefficients. Let's see the block diagram representing the Wiener filter. So this is a typical block diagram representation of Wiener filter. In this, if you see this Xn is the observed signal. It consists of a real signal and noise. That means it is a combination of both the actual signal and the noise. We pass this signal through a tab delay line filter, which is a kind of FIR filter. From this, we will get the present as well as some past values of the signal, that means xn, xn minus 1 with the help of these delay elements. They are then multiplied with respective weights. As you can see in this xn, we say it is multiplied with W0. Similarly, up to last xn minus m, we can say it is multiplied with Wm minus 1. So that means we have m number of weights, and then all these products are added to obtain the output, which is denoted by d delta n. This output is usually considered to be an estimate of some desired signal. So we are considering this desired signal as dn, and this d delta n is nothing but the estimate of this dn. Now if we subtract this, means if we take dn minus d tilde n, we will get some difference. So that is basically the error. We call it as estimation error. Now if we say that okay, our design filter is an optimum filter, that means this error should be minimum. For that, we can say that this En, which is nothing but the difference between the desired and the observed signal, is the optimality condition we want to achieve. Basically, we are not taking this estimation error as such. We are taking it mean square error of this. Now, let's see what are the basic equations we are considering for this Wiener filter. As we have said, this input is represented as xn, and we have tap weights from 0 to m minus 1 represented by w. So wi is nothing but tap weights, and output of this filter we are considering as d tilde n. Now how we obtain this d tilde n in equation form? You can say d tilde n is nothing but the convolution of input and the tap weights. So we get the equation number 1 as d tilde n is equal to summation k is running from 0 to m minus 1 wk into x of n minus k. If you notice here, this wk or wi, if I say all the tap weights, are nothing but the filter coefficients. We can also call that as impulse response of the filter. In this, also one thing we should notice, that w is not dependent upon time. It is independent of time. K is just representing by which part of input, means present, or which past value we are multiplying that with that corresponding weight. So from this we can get the estimation error is nothing but dn is our desired signal and d delta is what we have achieved as output of the filter. So En is equal to dn minus d tilde n. Now let's represent this equation in matrix form to simplify the operations. We can say this W vector, which is nothing but the vector m cross 1 column vector corresponding to the tap weights W0 to Wm minus 1. Similarly, this x vector n is the combination, or I can say again m cross 1 column vector of in present and past values of the input, that is xn to x of n minus m plus 1. Then how we can obtain the output d delta n in matrix form, that is nothing but the dot product of the input and the vector tap coefficient matrix w vector transpose into x vector n. Also we can write it as x vector transpose n into w vector, because that is a commutative kind of operation. And with keeping these values in the estimation error, we can obtain the estimation error as dn minus, by keeping this value of d tilde n, we can obtain w vector transpose x vector n as this estimation error. Now, what is our objective? What will be the objective function? So, let's define our objective function. Now, Wiener filter theory estimates the tap weight sequence that minimizes the mean square value of the estimation error. We are calling it as minimum mean square error, that is MMSE. And if I talk about mean square error, that means MSE. So, we have to minimize the mean square value of the estimation error. So, how we can compute that mean square error? That is, we are representing by j. Again, j is nothing but it is the function of tap weights, because only tap weights are which we can control. So, it is given as the function of tap weights, it equal to expectation, that is again mean of the square of that estimation error. So, we are defining it as mean square error. Why we are calling it as, means why we are taking that expectation? Because we are considering that our input as well as the desired signal both are the real coefficients, both are real. If we say it is complex, then we have to take the mod, but here we are considering real signal, so it is just e square n, and we are taking expectation because that is stationary, and we have to take the average. And also these are random values, input is random, dn is random, and also this error will be random function, so we are taking the expectation operator. Now if we substitute in this the value of en from equation number 6, it will be such kind of equation, that is expectation dn minus w transpose or w vector transpose x vector n, and dn minus x vector transpose n w vector. And if we solve this, if we multiply both these terms, you will get the equation number 7 in this form. So it has 3-4 terms. Now we will discuss each term individually, what is this first term, second term, third, fourth represents. So starting with e d square n. If you say this is the desired signal, dn is nothing but the desired signal. So expectation d square n is the variance of the desired signal. We can represent it with sigma d square, and we are assuming that mean of this is 0. Now next is another term, which is expectation of this cross correlation between the input vector and the desired response. Again, this will be a m cross 1 vector, and it is represented as theta. So it is expectation of this x vector n into dn, and it is theta 0, theta, it will have values like theta 0, theta minus 1 up to theta 1 minus m, and also we can write it as theta minus k, expectation of x n minus k dn, where again k is running from 0 to m minus 1. Other term is expectation dn x vector transpose n is nothing but the transpose of this previous term, which is expectation x vector n dn, and therefore if you substitute all these equations, and from this we will get theta transpose. As we got theta from the previous term, this is theta vector transpose. Now last term, if you see in the previous equation of the mean square error, it is expectation xn x transpose n, which represents the autocorrelation, because both are the input. So it is autocorrelation of input vector xn computed as the outer product of the vector with itself. It will be a m cross m matrix. So this will be a m cross n matrix, and if you see further, this m cross m matrix, we represent it with phi, that is equation number 10. Now how we can represent this M cross M matrix, what values it will have? So it will have the values running from phi 0 to phi m minus 1, and if you see the last row, it will have phi of m minus m plus 1 to phi of 0. Actually this product we need, this is a commutative kind of operation, and when we change the order, means phi of I minus k is phi of k minus I. So with this we don't need all the values, only phi 0 to phi m minus 1 values are sufficient. We can also say this phi of I minus k is nothing but phi of k minus a. As I mentioned, that is a cumulative kind of operation. So with this, the equation for minimum or I can say mean square error can be simplified by keeping all the values of the different terms. Now what is actually our motive? What optimal condition we have to obtain? Now to determine the optimal tap weight, that is noted by WO. This is not W0, this is WO, which represents the optimal tap weight, because we have seen this mean square error is a function of tap weight. So we have to minimize this, and to minimize this we will have some optimal kind of tap weights. As I mentioned, we can only control this tap weights. So we have to differentiate this equation with respect to the tap weights, and we have to set it 0 so that we can find the minimum value, and that will be a global minimum. This is kind of quadratic equation, so we will get the global minimum out of this, and we have to find that minimum weights, or I can say optimal weights, that is represented by WO, W vector O. Now let's talk about the derivatives. As we have seen in this equation of equation number 12, if you see mean square error equation, we have different terms. That means if we differentiate this equation, so we have to take the derivatives individually, and we will see what each derivative will result into. If I talk about derivative of sigma d square, because sigma d square, it will be a constant, because that signal is given to us with some variance. So that derivative will be equal to 0, and let's discuss the other derivatives. Now derivative with respect to tap weight of second term, that is theta transpose vector, that will be equal to theta, because W again they are the real coefficients, these are some constant values. Similarly, the derivative corresponding to next term, W transpose theta transpose, that is again equal to theta vector, and if you differentiate this W transpose phi W vector, it is nothing but 2 times, because that will be kind of square, so 2 times of phi W vector. And if we substitute all these derivatives in the equation of mean square error, you will get this equation, that is a derivative of J with respect to the vectors tap weights, that will be equal to minus 2 theta plus 2 phi W vector, and if I want to calculate the minimum, we have to keep this equal to 0, that is our equation number 17. Now by keeping it equal to 0, what we get is condition for the optimal filter, which is nothing but phi W optimal. We are keeping it because if we take this condition, what will be the W weights? W weights will be now the optimal weights, so we are representing it with W0 vector, and it is equal to theta. Now what is our motive? We want to calculate the tap weights. So for that, let's see another equation. Also this equation is known as Wiener-Hooft equation or the normal equation. Now let's discuss a little bit about this equation and how you can calculate this tap weights. So W naught, or I can say the optimal tap values, are nothing but phi inverse of theta vector. So this will result into a set of linear equations. If you see in expanded form, it is kind of this vector. We can solve this, and this will be a set of linear equations, m linear equations, because there are m tap weights, and you will get set of m linear equations to solve for all the tap weights. So thus we can say that minimum mean square error, by keeping this value of tap weight, optimal tap weights, we can find this equation number 21, which is nothing but representing the minimum mean square error, that is MMSE. And if you find the dimensionality of this equation phi, matrix phi, that will be nothing but M cross M matrix. Now let's see one example. Here ECG, this signal A, if you say that represents a ECG signal with noise. Now if I want to filter this using Wiener filter, I have to choose some reference which we call it as a desired signal. Now this signal B, if you see in this figure, it is that desired signal. How we obtain that desired signal? It is obtained as the piecewise linear model of the desired version of the signal obtained by concatenating linear segments similar to P, Q, R, S in T waves in amplitude, duration and interval in given noisy signal. So we are taking piecewise model of that from original signal. We are obtaining that reference and baseline of the model is set to 0. Now we are using this desired signal and we have original signal which is nothing but xn, and when we are filtering, when we are applying this Wiener filter concept, we are getting equation or signal C, which is nothing but the output of Wiener filter. So I hope you understand this topic. This is the reference we have taken. Thank you so much for this lecture.